Hello everyone. In this lesson, we will talk about LSTM or long short-term memory. And in this lesson, we will use FD004 dataset. And let's begin. Here, same parts. We will define the determinate useful life, and you can see the RU out. And here, X-terrain, Y-terrain clip part. Here, evaluation function, and here we'll fit linear regression model, and you can see the our base values, and here we will start. Here, let's begin. And what happens here? This code focus on adding operating conditions to the dataset and scaling the data based on these conditions. And let's talk about what happens here. That operating condition function creates a new data frame df underscore op underscore cont as a copy of the input data frame date, and it runs the values of setting 1 to the nearest integer and setting 2 to the decimal places, and it creates a new column op cont by concatenating the string representation of setting 1, setting 2, and setting 3 with underscores separating them. And this new column op underscore cont represents a unique operating condition based on the settings. And why we do that? The operating condition is an important feature because engines might behave differently under different settings. By categorizing these settings into a single operating condition, the model can better understand and account for the variations in engine performance due to these different conditions. And this step helps in identifying the specific condition under which engines are operating, which is important for accurate predictions of the remaining useful life. And let's look at the other part, condition scaler, and what happens here. Let me select, let's start. Okay. The function condition scaler applies standard scaling to the sensor data within each unique operating condition, and it initializes a standard scalar object for each unique operating condition in the training data df3. It fits the scalar on the sensor data corresponding to that condition, and it transforms the sensor data in both the training and test dataset based on the scaling parameters learned from the training data, and the function returns the scale training and test data frames. And why we do that, that part. Standard scaling is essential, that, to ensure that the data for each sensor is normalized, which helps the model learn more effectively, and it ensures that each feature contributes equally to the model's learning process. And by scaling the data within each operating condition, the model can better capture the differences between conditions. This is important because engines might operate differently under different settings, and normalizing within these groups allows the model to learn these patterns more accurately. And here, X-terrain condition, X-test condition, and scaled, we will combine both parts. First, here at operating condition with X-terrain, this part applies the add operating condition function to both the training and test dataset to add the operation underscore condition column, and it then applies the condition scaler function to scale the sensor data within each operating condition for both training and test sets. And why it is important, combining these two steps prepares the data for the LSTM model by ensuring that the model is normalized and categorized based on operating conditions, and this preparation is essential for achieving accurate and reliable predictions of the remaining useful life of the engines. And I think it's okay, and let's look at the another parts and what happens here, and let's talk about. We will plot sensor data, and let's talk. The plot signal function is designed to plot the sensor signal against the remaining useful life, and you can set the figure size here. Let's look at the if else parts. What happens here? If no specific unit number is provided, it plots a signal for every 10th engine in the dataset. This is done to avoid cluttering the plot with too many lines, and the x-axis is set to count down from 250 to 0, representing the remaining useful life decreasing to 0, and labels. You know that the y-axis is labeled with the sensor name, and the x-axis is labeled remaining useful life. And let's look at these parts and what happens here. These loops here iterates overall sensor names and calls the plus equal function for each sensor, and it plots the scale sensor data against remaining useful life for each sensor. And what we can say here, we have a lot of signals plots here, and by the way, you need to check them manually and yourself, and it will be your homework. And let's switch. I took some notes and we will talk about them. For the sensors 1, 5 and 16 and 19, we can say that these sensors look similar to each other, but does not seem very useful. For example, like that, 19. And these sensors do not show any clear trend or pattern that changes consistently as the engine approaches failure, and because of this they don't provide useful information for predicting remaining useful life. And for 2, 3, 4, 11 and 17, and let's look at the 17. These sensors show a similar upward trend, and these sensors consistently increase as the remaining useful life decreases. This means they are useful for predicting when an engine might fail. We should include these sensors in our model because they provide valuable information. And for for 6, 10 and 16, these sensors do not show much of a trend, as you can see here. These sensors don't change a meaningful way as the engine approaches failure. Since they don't help us predict remaining useful life, we'll exclude them from our model. And for sensors 7, 12, 15, 20 and 21, and let me switch. Let's stop at 20. Okay, what we can say, these sensors clearly show the difference between the two types of failure being developed, and these sensors can differentiate between different types of engine failures. This makes them very useful for our model because they help identify the specific failure mode, leading to more accurate predictions. And for 8, 9, 13 and 14 sensors, and let's look at the 14, this nearest sensor. Okay, these sensors show similar patterns but with added noise from fault conditions, and while these sensors show some patterns, the added noise makes it hard to distinguish between different types of failures, and this could confuse our model. We need to test the model with and without these sensors to see if they should be included. And for example, another sensor 18, this sensor does not seem to hold any useful information after standardization, and after adjusting for operating conditions, this sensor does not show any meaningful pattern, and it does not help in predicting remaining useful life, so we will leave it out of our model. And let me switch and let's look at another parts, and here remaining sensors. It selects the sensors that are considered useful based on the earlier analysis and excludes the ones that are not useful, and to ensure that only relevant features are included in the model, which helps in improving the model's performance and reducing noise. And let's look at the exponent exponential smoothing function. And what happens here? This function applies exponential smoothing to the sensor data and drops at the initial samples to reduce filter delay. And exponential smoothing helps to reduce noise in the sensor data by averaging it over time, giving more weight to recent data points. And dropping initial samples helps to avoid the artifacts introduced by the smoothing process. And here we have a GSS. What is this? You know that we talk about. This function splits the data into training and validation sets using a group shuffle split to ensure that all records of a single engine are assigned to either the training or validation set. And to prevent data leakage, if records the same engine were split between training and validation sets, the model might learn to interpolate between these records rather than generalizing to new engines, leading to overly optimistic performance estimates. And I think it's okay, and we can switch and we can continue from that. And what is this? What happens here? The purpose of this code block is to create an example data frame that mimics the structure of our sensor data for further demonstration and testing of the data pre-processing and sequence generation. And let's look at unit number. What is this? This column indicates the unit or engine number, and the first 5 rows corresponds to engine 1, and next 5 rows correspond to engine 2. And what is X here? This column represents some sensor measurement. For simplicity, values are incremented by 0.2 for each subsequent row. And here Y, this column represents the target variable, and the values are slightly decreasing to simulate a trend. And example df designs, here example df equal pd data frame data d. This line converts the dictionary d into a pandas data frame name explainable example df. And example df, this line outputs the data frame to display its contents. And I think it's okay. And let's look at our giant train data and what happens here. Let's talk. The purpose of this code block is generate sequences of a specified length from the input data, and this is important for training long short-term memory networks which require sequential data as input. And first let's look at this part, first 3 lines. Data here, it extracts the values of the specified columns from the data frame df and stores them in a numpy array. And num elements, what is this? It stores the number of rows in the data array. And let's look at this part. We have a for loop here. And what is this? First, let's look at this part. Zip range to here elements +1. What happens here? This creates pairs of start and stop indices for slicing the data array. And what we can say another for range 0 num elements sequence length -1. This part, let me select. Okay, it generates start indices. And let's look at this part, sequence length num elements +1. It generates stop indices. And here yield data. What is this? Yield slices of the data array, each of length sequence length. And let's look at this part, gen equal gen train data. And what happens here? The first example df at equal 1 with df unit number. What is this? It filters the data frame to include only rows where unit number is 1. And sequence length, what is this? It specifies that each sequence should be 4 rows long. And columns x, it specifies that the sequences should be generated from the column x. and list gene. It converts the generator object again into a list to display generated sequences. And let's look at first sequence here. Okay, this sequence includes the first 4 values from the X column for engine 1. And let's look at this second sequence. This sequence includes values from the second to the fifth row in the X column for engine 1. And I think it's okay. And let's look at the another part. And we have a function called gene data wrapper. And what happens here? The purpose of this code block is generate sequences of data for multiple units and concatenate these sequences into a single NumPy array. And this is particularly useful for training machine learning models that require a uniform input shape. And first, let's look at these 3 lines. And okay. What happens here? First unit narrates what is this? An array to specifies which units to generate sequences for, and if not provided, it defaults to all unique units in the data frame. And what is this? What happens here? It checks if the unit numbers array is empty. If it is, it assigns all unique unit numbers from the data frame to unit underscore NRS. And here, this part, what happens here? First data gene, the generator expression that creates a list of data sequences for each unit specifies in unit numbers using the gene train data function. And let's look at this part, np concatenate and another parts. It concatenates all generated sequences into a single NumPy array and converts the data type to a float 32. And let's look at this part. And sorry, wait, data array. And okay, let's look at this part, data array. What happens here? The resulting concatenate arrays of sequences. And let's look at these parts and what are they. First, here sequence for unit 1 here. This sequence includes the first 4 values from the X column for unit 1, and second sequence for unit 1 here, as you can see. This sequence includes values from the second to the fifth row in the X column for unit 1. And let's look at this part. What is this? This is the first sequence for unit 2, and this sequence includes the first 4 values from the X column for unit 2. And here, second sequence for unit 2. This sequence includes values from the second to the fifth row in the X column for unit 2. And I think it's okay. And let me switch to another part. And we have a function def gene labels. What happens here? The purpose of this code block is to generate labels for each sequence of data for multiple units, and these labels are important for supervised learning models where the model learns to predict the label based on the input sequence. And let's look at this part first. What happens here? What we can say here, a data matrix, it extracts the values of the specified label column from the data frame, and num underscore elements, what is this? Determines the number of elements, I mean rows, in the label data. And return part data matrix sequence length -1. What happens in this line? It returns the label data starting from the index sequence length -1 to the end, and this ensures that the label corresponds to the end of each sequence. And another function, gene label wrapper, what happens here? And let's talk again, unit underscore NRS. What is this? An array to specify which units to generate labels for, and if not provided, it defaults to all unique units in the data frame. And here label gene, what is this? It is a list comprehension that generates label for each unit specified in unit underscore numbers using the gene underscore labels function. And here LP concatenate, what is this? With the other parts. It concatenates all generated labels into a single numpy array and converts the data type to pull-out 32. And what we can say another here label equal gen labels. And what happens here? Let's talk sequence length for label y. Okay, everything is okay. It calls the gen labels function for unit 1, specifying a sequence length of 4 and using the y column for label generation. And it's okay. And here gen label wrapper, it calls the gen label wrapper function for all units in the example data frame, specifying a sequence length of 4 and using y column for label generation. And here labels for unit 1, these labels corresponds to the end of each sequence generated for unit 1. For a sequence length of 4, the first label corresponds to the fourth element, and second label corresponds to the fifth element in the y column. And here, what happens here? These labels include the end of each sequence for all units. The first two labels corresponds to the unit 1, and next two labels corresponds to unit 2. And I think that's okay. And let's switch and what happens in these lines. And let's talk what we can say here with these parts. The purpose of these code blocks is to generate sequences of test data that are of fixed length, even if the original data is shorter than required sequence length. This is important for ensuring that the model receives input sequences of consistent length. And let's look at these parts A, B, and what happens here with NP full. A here a 5-3 array filled with minus 99 and NP full. And B, what is this? It is a 2-3 array filled with 0 and IDX, what is this? The index where array B will be placed in array A calculated as difference in the number of rows, and A IDX at equal B, what is this? It replaces the last rows of A with the rows of B, and you can see the output here. And let's look at this part, div and def gene test data, and what happens here. Let's look at the parameters, I mean input parameters. df here the input data frame containing the test data and sequence length. What is this? The desired length of the sequence, and here columns, the columns of the data frame to be included in the sequence, and mask value, the value to fill in if the data frame has fewer rows than the sequence length. And what is the functionality? Check if data frame is shorter than sequence length. And let's look at these parts. If data frame is okay, and here let me select 2 as okay. What happens here? If the number of rows in the data frame is less than the sequence length, a new array data matrix is created with the shape and filled with mask value, and the values from the data frame are placed at the end of data matrix with the remaining values at the beginning field with mask value. And what happens in the else part here? If the data frame has enough rows, the values are directly used. And let's stop these parts. What happens here? Start and stop are calculated to get the last sequence length rows from the data matrix, and the function yields the resulting data matrix. And let me switch and what happens here. Let's talk about this part. The purpose of this code block is generate sequences of test data for each unique unit number in the example underscore df data frame using the gene underscore test underscore data function defined earlier. It ensures that the sequences are of a fixed length, if even if the actual data is sorted by padding with the specified mask value. And what we can say, example df part, unit number and unique. What is this? It retrieves the unique unit numbers from the example data frame, and for each unique unit number it creates a list of sequences generated by the gene underscore test underscore data function. And what we can say, example df unit and equal unit number. What is this? It filters the data frame for the current unit number and sequence length equal of 6. It specifies the desired length of each sequence, and here columns. What is this? It specifies the column to be included in the sequence and mask value equal minus 99. It specifies the value to use for padding if the sequence is shorter than the desired length. And next gen retrieves the first sequence generated by the generator expression. And what we can say here, the output is a two-dimensional array where each row represents a time step in the sequence, and the single column contains the values of the x column from the data frame. If the number of rows in the original data is less than the sequence length, the sequence is padded with the mask value at the beginning. And let me switch, and what happens here, let's talk here, sequence length equal 20. What we can say, in this part, the purpose of this code is to pre-process the training and test data for a remaining useful life prediction model, which includes handling operating conditions, scaling, smoothing, and preparing the data for sequence modeling. And the code ensures the data is ready to be fed into a sequence-based machine learning model, likely an LSTM or similar type of network. And at the beginning here, train rule and clip upper 125 and implicit true limits the maximum remaining useful life value to 125 to prevent excessively large remaining useful life values from skewing the model. And clipping ensures that the target variable remains within a realistic range, improving the stability and performance of the model. And xtrain interim, what is this? With xtest interim, it adds a column representing combined operating conditions based on the other settings, and this helps in capturing the effects of different operating conditions on sensor readings. And condition scaler part, and what happens here, let's talk. Scales the sensor's data for each operating conditions to normalized data, and it ensures that the model receives standardized input, improving learning efficiency and performance. And we will apply exponential smoothing for xtrain interim and xtest interim. What is this? It smooths the sensor data to reduce noise, and smoothing can help in highlighting the underlying trends in the sensor data, making it easier for the model to learn from the data. And GSS, you know that part here. What's the purpose? It splits the data into training and validation sets, ensuring the split is done by unit numbers to prevent data leakage. And a group shuffle split ensures that the units are split into training and validation sets in a stratified manner, maintaining the distribution of different operating conditions. And I think it's okay. What we can say here, another part. train array. Let's look at this part, train split array, and continue to relation split array. What happens in this sixth line? It generates the sequences and corresponding labels for training and validation, and it uses the helper functions gene underscore data underscore wrapper and gene underscore label underscore wrapper to create sequences of the specified length for each unit, making the data ready for sequence-based models. And let's look at this part, train array and label array. Sorry, let me see this slide. Okay, it generates sequences and labels for the entire training set, combining all units, and it prepares the entire training set for model training, ensuring consistency in the data format. And again here, test gene. And what is this? Please stop. Okay, I selected all. Okay, we can continue now. It generates sequences for the test set, ensuring each sequence is of the same length by padding if necessary, and pad sequences with a mask value here -99 if they are shorter than the specified length, ensuring uniform input size for the model. And we will build the model, but let's stop here, otherwise the lesson will be long, and see you in the second part of LSTM.